I'm Robert Bradshaw. I work for Google, and I'm going to talk today a little bit about a project I've been working on called Apache Beam. So let's start a little bit about data. Obviously, if you're here, you're interested in data. And at Python, we have a lot of tools for manipulating data, for reading it in, for munging it, for analyzing it, for plotting it. And this great ecosystem has evolved around how do you understand your data? How do you do what you want with your data and get the information out of it? And one of the interesting things about data is data can be really big. When I say big, I mean really, really big. It doesn't fit on one machine. Not only can you not load it into memory, maybe you can't even fit it onto a machine that has, a stack of 10 terabyte hard drives. It's often distributed, and you want to understand and make use of this data. There's a lot of reasons that data is getting big these days. With the Internet of Things, processors are cheap, internet's cheap. You have mobile devices that maybe are pinging you about user actions, and or you have sensors out, all over some desert somewhere looking for seismic activity, and you want to be able to gather this data. Another reason you want big data is for machine learning. An analogy is if machine learning is a rocket, the data is the fuel, and if you don't have enough data, you're really just not going to get the results you want. Not only can data be big, it might be infinitely big, meaning you never see the end of it. It just keeps coming and coming and coming. And this is the streaming scenario where you're always getting more data, and you can't just say, okay, I'll wait until all my data comes in, and then I'll process it. You really have to process it as it goes. So at Google, what we did is we kind of started out with a company is like from the inception, we have data that was too big to fit on one machine. And one of the tools we developed early on was MapReduce. We published a paper on MapReduce in 2004, and this is kind of it changed the way that you think about big data processing. Instead of starting to think about machines and what they're doing and scheduling them, you really kind of step up a level and think about, okay, I just want to define what I want to compute and have an infrastructure that distributes the work and gives me my results. And we published this paper, and since then there's been a lot of development in the open source ecosystem. There's Hadoop, kind of the foundational thing, and then there's things like Flink and Spark and Drill and Hive. And during this time, we've also been iterating on this internally. So we have things like Bigtable and Flume and Millwheel and Dremel. And some of these technologies we've published about, and that's inspired open source projects that take their own ideas and mix things in. And we've been looking at this and saying, okay, well, we develop something, we use it for a while, then we publish a paper, and someone else has the same ideas and reads our paper and reads some other papers and develops something. And we're kind of developing these two parallel worlds. And so a couple of years ago, we had decided, instead of publishing a paper, let's publish some code that people can actually use. And this is Dataflow. It's a system that allows you to do big data processing. And then we had the idea, well, instead of just publishing the code, let's actually integrate with all these other great tools. So that's where Apache Beam arose. It arose from, it's kind of the combination of taking a lot of lessons learned from doing big data processing over the decades at Google and all the open source tools that you know and love and are familiar with. So the Beam model, it's kind of a step way beyond MapReduce. And the idea of the Beam model is it lets you focus on the abstractions, your application logic, and you can swap out the backends for different backends. Kind of one story about this. So at Google, we were trying to clean up some old users of MapReduce. And MapReduce developed over the years hundreds of tuning parameters, like every big system does. You can tweak this buffer, and you can tweak the timing on these RPCs over here. And so we're trying to go to clean these up, and we had teams coming back to us that said, no, you can't delete this flag. We need it for our pipeline to be able to go on time. And we would tell them, that flag has been a no-op for years. And this is not an isolated occurrence. So what happens is when you tie yourself to a system, you tune for the system. You have some expert that comes in and says, oh, my pipeline is too slow. I know how to tweak that. And you get it running really, really well in the system. And as the months go by and the years go by, your data profiles change, your pipeline itself changes, the underlying system changes, the tuning parameters never change. And worse than that, someone says, oh, this is the magic go faster flag. I'm going to use that on my pipeline too. And you end up with these complicated pipelines that have these tuning parameters built into them that are maybe relevant at the time, and a lot of expertise went to go into them, but 90% of tuning parameters are obsolete. If not now, they will be in 6 months. And so we want to completely abstract away the back end from the front end. The other thing we've realized is that batch and streaming processing, we want them to both be first-class citizens. So instead of thinking, okay, I want to do a batch job, so I'm going to do against, program against, say, Spark RDDs, and someone else says, okay, now we want to do a streaming job. We're going to write this completely separate pipeline that hopefully, cross our fingers, computes exactly the same thing, but is completely rewritten, and then evolve these two pipelines in parallel. Instead, we want to have one framework that does both. And kind of one key concept for streaming that we've introduced is this notion of trying to separate event time from processing time to be able to have strong consistency guarantees even in a streaming system. So without further ado, here is an example pipeline. So like Dask before, everything in Beam is deferred. So we create a pipeline object, and you just put it in with context, with pipeline as P. There's our pipeline. And now what you want to do is you want to read some data in. So here we might read a text file. We might read several text files. We might read several text files that are sitting on maybe GCP or something like that. And lines is a P collection. Again, this is very fast because nothing actually happened. But what we do is we now have a virtual collection of all the strings that represents all the lines in all those files. And now what we do is we want to split those into words. This is going to be a word counting example. And what we do is we have a flat map, and we can pass this lambda that here is just a regular expression that says, okay, look for things that look like words. And we want to take every line and omit all the different words. And this pipe operator here is kind of a new syntax. We played around, and we never found a syntax that was like perfect. But this one's pretty good. So if you just put your mind in the mode of, I'm at a bash prompt, and I take the thing to the left of the pipe operator, and I'm streaming it to this operation on the right, and I'm getting something out. In this case, I'm getting words, which are all the words in all my data files. The nice thing about this pipe operator is I can chain it. So I can say words. Now I can map these things. I have words. I can pair them with the word and one, and then I can do a combine per key, where I just say I want to sum all these ones together corresponding to each word. This word, the first element in the tuple is the key, and the second element is the value. So what happens when this executes is it automatically knows in the combined per key that the sum operation is commutative and associative. And when it's doing a distributed job, it will lift the summation to happen on the partitions and then only sum the final result on a separate reduction step. And depending on the back end, we have a lot of abilities to actually dynamically decide the partitioning algorithms. So if you have some files that are big and some files that are small, it'll start reading all of them. And then the ones that are too big, it'll actually say, oh, this file turns out to be too big, but I got some idle workers over there. Let's give the second half of this file to someone else. And so everything kind of completes at the same time. Of course, results aren't any, oh, yeah, and one more thing is you can actually define your own composite operations. So this is another reason for doing the pipe operator, is it means that all operations, whether built in, whether inlined here, whether from some third-party library, are all on the same footing. So in one of the inspirations for Beam was something called Flume Java, and we have Flume C++ as well in Google. And we had this P collection, and we kept adding methods to it and adding methods to it. And it became this like 5,000-line monstrosity. And that's only because we pushed back on 80% of the requests of, well, I want to add my special compute quantiles ignoring even numbers operation to your P collection. And so right now what we do is every single thing is on the same level. So this count is something that you can define as a composite operation. The other nice thing about composite operations is it actually gives structure to your graph. So when you're visualizing your graph, you can visualize the high-level things. It's kind of like functions, and then you can open up the operation and see what's inside there and see what's inside there. So you really have this tree, this hierarchical tree of operations for understanding when you're visualizing your graph or when you're debugging your graph. You're saying what step takes a long time. We can say this count step. Okay, we could go inside that count step and say what in the count step is taking a long time. Oh, it's the shuffle step, and so on. Also, counters and things like that are hierarchically organized. So you can build these massive pipelines that have, we have pipelines with thousands of stages, but they're comprehensible because maybe there's 10 top-level stages, and you can drill down into each of those or ignore ones that you don't care about. So, of course, it's no good if you don't actually write your results out somewhere. So this is the final step, is to write them. This also shows that the computation is generally a DAG. It's not just linear. Linear is nice because you can chain things together, but you may do a DAG, you may join things together, you may split things apart. And then when you exit this context, the pipeline actually executes. So we've shown how to kind of create the DAG. What about streaming? This is one of the key concepts is we introduce streaming in a way that's minimally invasive to the batch pipeline. So here's our batch pipeline we constructed, and here is the streaming version. We have to read from a streaming source if you want to do streaming. I guess it is possible to read from a batch source and do streaming, but that's not interesting because then you just finish. And then also you have to specify this windowing operation that specifies how your aggregations occur. So let's look at that windowing in a little bit more detail. So one thing in API design is you want to have somewhat of a separation of concerns. So the first concern is what are you trying to compute? And then in streaming pipeline you say where in event time are you computing this? When in processing time are you materializing this? And then the last question is how do results relate to each other? So processing time versus event time. I have to credit the data artisans folks we work with on Flink for this analogy. It's kind of like Star Wars, where you have the direction of causality in the universe, and then you have the direction of causality in our observations. And these two are not necessarily in the same order. In fact, they could be decades out of order. And you have to reason about these two things separately to be able to have a notion of completeness. So what we can do is we can put these on separate axes. And we say, a long time ago is the direction of causality in the Star Wars universe. And then we have our universes when we observed the events. And you can kind of see it's not quite linear. There's a light cone that goes up here that, we can't observe the events before they happen, but we may observe the events long, long after they happened. So we're going to kind of use this diagram to understand how the aggregation happens in windowing. So the first question is what we're going to compute. This is kind of a little tiny snippet of our pipeline where we say we want to compute the sums per key. And remember, this is a reduction that happens partly on the mappers, partly before shuffle, partly after shuffle. And the typical batch operation is we have a bunch of elements come in, and we kind of just observe them sequentially, and the final result here is 51. And we saw a total sum of 51. That's all our elements that we ever saw ever. And this is kind of the typical batch pipeline. Now, if we want to do something in streaming, we want to say, well, we want to group these things into windows. Here we're grouping these things into 2-minute windows. What we're going to do is we're going to publish a result per window. So in this first window we saw 14, in the second window we saw 22 as a sum, 3 and 12. And right here what we do is we say, this is where in event time, and you notice no matter, even though the elements themselves came in different orders, we now have correctly, the time from 202 to 204 has the correct sum there. It doesn't matter when the elements came in, when we observed them. All that matters is when they really happened. We're summing with respect to this. This is our robustness. But to publish the results sooner, one more thing about windows is we not only support fixed windows, but you can also do sliding windows. So you can say, I want this result to accumulate in multiple windows. And we also have windows are UDFs, so you can actually specify your own windowing functions, and they need not be the same per key. So you can actually define, say, session windows, which says, I want my window, my aggregation to happen with respect to a session that's defined by elements that are separated by a gap no more than 20 seconds, or something like that. And everything is happening per key, so on different keys you may actually have different sessions. Say if your keys are users and your sessions are visiting a site. So the other thing about windowing is it happens at the aggregation, but you actually specify, you tie it to the P collection. This is key to allow your windowing to work well with composite operations. So when I window, for instance, by fixed windows, now when I do a sum per key and then say I follow that up by saying I want to have the largest 100 things, I don't have to re-specify my windowing. My windowing is the same as the windowing I had before. And this allows us, if we have some composite operations that deeply nested says I do a sum, well, it now does the windowing according to that windowing that was specified up above. And your pipeline can have multiple aggregations and multiple windowings throughout the pipeline, and kind of the windowings enclose a portion of the DAG of your pipeline. So now we want to understand, well, when are these results actually computed? Because for a streaming pipeline, you can't wait for all the data. You have to say, at some point, I'm going to emit something before I've seen all the data, and this is the notion of a watermark, where this green line here gives us a heuristic of when the system says, I think I've seen all the data I'm ever going to get for this window. And once I think I've seen all the data I'm ever going to get for this window, I'm going to emit that window, and so the downstream processes can consume it. But I might have partially complete windows that I'm going to hold on to until I'm sure that I've seen all the data for them. Now, in a distributed system, if we have correct watermarks, if we can actually say this works great. But sometimes our upstream doesn't always know. For instance, if I'm collecting data from mobile devices, someone might have been sitting on an airplane And if this is a mobile gaming application, when they land and they reconnect, now suddenly some data comes in that, oh, they popped 9 bubbles on my fancy new gaming app. And this might have come hours later. So we have to have this notion of, well, what do I do when I was wrong about my estimates of when I've seen all the data? The simple model says, well, I just reject anything that's too old. I got enough data. But if you want to be more complete, the model also extends to say, well, I can actually say if I've seen more data, or if I can actually emit results before I even have seen all the data, and specify how I want to accumulate and how I want those results to belong to each other. So this is kind of the model that allows us to reason about streaming things in a concrete way without affecting, notice this yellow line here has not changed, what I'm computing. So this yellow line could be some giant, enormous pipeline, and all I have to specify is how I want my aggregations to perform, and this percolates all the way through. And so here's an example of this this how refinement. So notice that when I hit this 14, this 9 up here, I emit a new result and say, actually, it was 14, not 5. And likewise, in the second window here, this 7, I say, well, so far I've seen 7, but it's not everything. And then when I finally emit the window, I say, actually, the final result was 22. If you're actually going to persist this one, maybe bill someone on it, that's what you would do. So this notion of dividing things into what you're trying to compute, where in event time, what your windows are, when you're going to try to compute it, say you're going to try to compute it, you can wait for everything, or you're going to wait till you think you've seen all the data with some probability of success, and then how the results relate to each other really allow you to separate these concerns. And you can kind of mix and match these different pieces together to get the results you need. One of the important things is you can trade off latency versus correctness versus cost by varying these different parameters, and different applications have different uses for these. This is just kind of a short overview, but there's more information at the Beam site. And another thing to note is all of these things actually work in batch too. This isn't just streaming. If I wanted to group by session windows, I can do that in batch too, and it just works just perfectly. The advantage of batch is you usually know when you've seen all the data, which is you've read all your input files. So you don't have to worry about late data coming in if you're in batch. But all of these concepts work just the same. So what does Apache Beam provide? So it provides this model for dealing with streaming data and batch data in a consistent way. The other thing Apache Beam is it's a set of APIs for actually rewriting these pipelines. As we saw, there's a Python API. There's also Java API that actually came before the Python one. And then the other thing that Beam provides is a swappable set of runners for actually executing on distributed backends. So we have a backend for Apex, Flink, Spark, Google Cloud Dataflow, and in-process testing, where if you have a bug, it just drops down in PDB and you can debug it right there, or do your unit tests. And you should be able to swap out these backends, and the computation you do remains entirely the same. And but you might have, for instance, different performance characteristics, or you might have different preferences about running on the cloud versus running on your local cluster versus running on a local machine. This is kind of the vision we have for Apache Beam, is we have multiple SDKs that are possibly in different languages, and then we have a single common representation for what is a Beam pipeline. And we take this representation and we send it off to the runner of your choice. And this runner of your choice then goes off and executes it. And then we have a portion of the we call it the fun API. It's FN, but it is kind of fun to work with. And it actually calls back into the SDK in an efficient manner to call your UDFs with appropriate batching and fusing so that you don't pay an enormous amount of serialization overhead. And so, of course, if I have a vision slide, it's only fair I say, what's the current status things? We're not there yet. But batch for Python actually exited beta just this year. It was in May. And so this is really exciting. Java has been out for a little bit, and we just recently got Python. And the alpha for Python, the streaming for Python is still in alpha, but we're trying it out now. It works. And we're also adding support for different runners. So right now the local runner works and the Dataflow runner works, and we're working with the Flink team to get that runner working. And as part of that work, we're fleshing out the fun API. So pretty much it'll be plug and play, match whatever runner you want with whatever SDK you want, and things should just work. Another point is that we're actually used as part of TF Transform for TensorFlow's preprocessing solution. So like I mentioned before, if data is kind of the rocket fuel, one of the important things with training is you got to have good data. And so usually when you're doing machine learning, you end up spending upwards of 80% of your time doing feature analysis, doing scrubbing, getting your data into good shape before you actually feed it into the model. Otherwise, you're going to get garbage out. And TensorFlow Transform is kind of a library. It's a suite of tools that uses Beam to do this pre-processing. You basically write a Beam pipeline, and as part of your pipeline, you define these pre-processing funds. And the nice thing about TensorFlow Transform is that it spits out, in addition to your pre-processed data that's sitting there, ready to be trained on, it spits out some artifacts that you can use then at serving time to guarantee that there's zero skew between your pre-processing that you execute at serving time and the pre-processing that you executed prior to training. This may sound trivial, but it's surprisingly easy to get wrong, where if your serving infrastructure is different than your pre-processing infrastructure and there's skew, this can actually create enormous problems for your model. So you can learn more. There's Beam is a top-level Apache project. There's some good blogs on the O'Reilly blog about this kind of streaming idea that really go into detail about how you can tease apart these notions of windowing and triggering and when things happen. And of course, we've got user lists and mailing lists and a Twitter account and all that kind of stuff. So thank you.